Okay. Great. Okay. All right, so let's keep cell phones out of sight, put them away. Canvas, obviously we'll be using Canvas a lot. I'll put all the recordings, PowerPoint presentations. Make sure that you sign up for notifications on Canvas for announcements. So if I post a homework or reading and I want you guys to know about it, if anything I need to communicate to you, I'm going to do it through announcements on Canvas. Make sure you get an email or you're checking it regularly or a text message, whatever. We'll have a schedule posted on Canvas as well. So each week we'll have a module, and then you'll see, okay, here's the readings I need to do, here's the homework assignments, etc. Don't figure out office hours, I'll let you know. We'll have software. Heck HMS runs on Windows. If you don't have Windows, you'll need an emulator, or I'm pretty sure it's on the computer lab. So let me know if you need access to Heck HMS on the computer lab. Pretty sure it's installed in the informal computer lab as well as these computers. I need to double check that. Finally, I encourage you guys to work together. You can have Zoom accounts through CU Boulder, probably CMU too, I don't know. Get a Zoom account and use that for group work sessions if you're not going to be meeting in person and working together in person. Okay, so for today's lecture, we're going to talk about hydrology as a discipline. What does it mean? What does hydrology mean? What does that cover in terms of science, engineering, and policy? We're going to be touching on all these subjects. The first part of the course is going to be, well, I think for every topic, I'm going to cover kind of the sciencey stuff of hydrology, and I'm also going to cover the engineering, which is like, how do we actually model it, measure it, calculate it? And then the policy is just, how does this affect our lives, and how do we manage risks, floods, water supply, that sort of thing. So today we'll talk about we'll quantify the global distribution and flux of water, talk about how it's spread across our planets, and then we'll define the basic components of a water balance. So you think about water coming into a watershed, water leaving a watershed. And then we'll talk about how do we delineate watershed boundaries if we have time. Okay. So what is hydrology? It's science, it's engineering. There's some hydrology science. This person taking a sample for water quality at some source water in Rocky Mountain National Park. And so looking at the nutrient concentration in it. Here's people digging a snow pit on the Grand Mesa. They're going to measure how deep the snow is, what its density is. You can calculate the water content of the snow. This is a snow water equivalent, is probably the most important hydrologic metric or parameter that we can measure in the Rocky Mountains. This is our water supply for everything, agriculture, drinking water. It is looking at floods and rivers. This is my technical area expertise. There's a floodplain restoration project in Fort Collins, just downstream of the Shields Bridge. And in order to design that project, they needed to know how much water would be coming through during the springtime at a certain recurrence interval or probability, so that they could tear the levees down and get a certain elevation so that this flood water could access the floodplain, make these cottonwood trees grow and attenuate flood peaks downstream. It's also understanding when we're going to have droughts, how frequent and how severe droughts are going to be, and floods, so that we can design infrastructure. This is a reservoir outside of Raleigh, in Durham, in North Carolina, during the 2006 drought that they had. That drought was broken by a hurricane. Colorado doesn't get hurricanes to break droughts, which is sad. Or maybe not sad, I don't know, but it's nice to have something to break a drought. Right now we're stuck in a drought. Also designing infrastructure. This is a dam. We need to know the flow rates that are going to come down this dam to design energy dissipation structures. So here we're measuring water, and there's a lot of ways we measure water, and there's a lot of reasons we measure water. The Usgs gauge right here, I think this is, can't remember exactly what this is. Anyway, maybe the Gunnison River. This is, it records the stage of the river at 15-minute increments, and then someone's going there every so many months to measure the discharge, correlate that with the stage, and then we get a discharge record through a regression analysis. Here's an old school gauge. This is a research watershed in North Carolina. There's a little flume right here where they can measure the depth of the water and get a discharge rate. It's also turning a wheel, which is an old school way of measuring the flow that's coming out of there. Why do we care about flow? Well, we want to know how much water is coming into our reservoirs, how much water our rivers have, so that we can plan for the year. So here's, I think this is one of the Gunnison River reservoirs, maybe Blue Mesa. So groundwater, surface water is easy to think about because we see it when it rains. If it ever rains again, we see the water that runs off. We see the water in the river. We see the rainfall. But groundwater is supremely important in Colorado as well as other places. This is the San Luis Valley in south central Colorado, and they have a big old aquifer that the farmers rely on. It's replenished by the mountains, the Sangre de Cristos, the San Juans on this side. And people are spending a lot of time studying how deep is that water, how thick is that aquifer, how much water can we take out of it on an annual basis? Do we need to have restrictions on pumping that groundwater out? Not only does it fed by the streams and mountains around it, but it also feeds the Rio Grande River right here. And so the flows of the Rio Grande are connected to how much pumping is happening in the groundwater. And we are obligated to send so much water down to New Mexico and Texas. So it has to be managed in an integrated way. So specifically, hydrology is the study of water and energy fluxes. And I say energy because the water cycle is driven by the sun's energy, right? We evaporate water from the ocean and from trees and grass, and that goes into the atmosphere, rains down. That whole process is fueled by the energy of the sun. So not only are we tracking where water is, we're looking at where energy is and how that's distributed in space and time. It's stored in the environment as well as the built landscape. So we're talking about urban hydrology and then natural, quote unquote, hydrology. So there's a lot of different disciplines within hydrology. You could be someone who models water at a global or continental scale for climate change modeling or for understanding how water is distributed around the planet. There's a satellite up there in space called GRACE, and it's going around, there's two of them, and it goes around the planet, and because water is really dense relative to other things, where there's more water, one of the satellites goes a little bit down because of the gravitational attraction. And they're able to measure the distance to like nanometers with a laser between these two things. So someone has this satellite data that's able to look at the distribution of water on the surface and in the ground across the planet at these like kilometer scales. And they're using that data to look at how that's changing over time as our planet, heats up and as the distribution of water changes. Urban hydrology is kind of more in the realm of engineering. There's a lot of, as an engineer, designing infrastructure, designing developments, going to do a lot of basic urban hydrology calculations. And we also need to study how, as we build, how water is distributed differently and how we might mitigate that. Because, well, we could go build a parking lot and then build a pond, so all that pollution and increased peak flow doesn't go down into a river or gully and cause erosion. We could also look at ways to infiltrate that water more in place and so that we don't have that big contribution to runoff that urbanization typically has. And I won't go through all the lists, but people specialize in groundwater, people specialize in snow, people specialize in rangeland forestry hydrology, as well as floods. So let's look at how water is distributed in the globe. Just from a mass balance standpoint, most of the water is in our oceans, right? 96.5%. So this little tiny blue sliver is our fresh water. Very, very small amount. Of that fresh water, most of it's frozen at our ice caps, at our poles. So 1% of 2.5% is in surface water, lakes and rivers. All right. Of that surface water, we still have some more snow and ice. I don't know what that means exactly, but we have 20% of that teeny tiny amount is in lakes. We have a teeny tiny amount in rivers. We've got wetlands, soil moisture, just water that's in the soil, right? That's a really important component of the water. So all in all, we have very, very small amount of water, surface water or fresh water available to us. So it's a really important resource. Here's what that percentage looks like visually. We've got, here's our planet. We take all the water out of the oceans, make it into a sphere. That's what it looks like. Here's the total fresh water right there. And here's the fresh water that's readily available to humans. Little tiny, tiny drop. Pretty crazy. All right, so there's a lot of ways to look at how water is distributed across the globe. Here's a paper that is looking at water supply relative to population and climate change. So if you think about climate change changing where water is, some areas are going to be drier, some areas are going to be wetter. And then you look at population change over so many years. I think this is 100 years. Where is populations growing? Where are they shrinking? Then you can see where we have potential water shortages relative to population change and climate change. So climate change has a signal on water supply. So blue is more water, red is less water. Population change, as populations increase, we have potential stress on our water resources. And then here's when you put the two together. So a lot of things are changing. It's not just climate, obviously, where people are living and using water is also a big part of the picture for our water supply.
That's in Colorado, water
right here.
Because of climate change.
Yeah, like this is like a global kind of thing. I wouldn't take a specific point as relative. We'll talk about what's going on in Colorado, and we're not getting more water. I can tell you that much. At least not on the western slope, because of climate change. So here's what a water balance looks like, and this is a flux of water. Values are 1,000 cubic kilometers per year. So just think of them as kind of relative numbers. So on average, this is how much water is evaporating, 425,000 cubic kilometers a year coming out of the oceans. And then we have evaporation, about 70,000 are coming out of lakes, forests, grasslands, everything like that. So most of our evaporation is happening in the oceans, although we have a pretty good amount happening over the land. A lot of that, a big percentage of that's coming back into the ocean. So it's kind of it's coming out of the ocean, it's going back into the ocean. But of course, some of that's going back over the land. So 385 going back over the ocean, 111 going back over the land and precipitation. And then we've got runoff, groundwater flow. When those are compartmentalized differently, we don't have those numbers here. Oh yeah, and then at any given time, 40,000 cubic kilometers are in the air. That's in the clouds, right? So water vapor is just floating around on average and hauled up there. We'll talk about cloud seeding when we talk about snow, and that's a way that people try to get some of that water vapor down to the lands that wouldn't otherwise fall. And it actually works. All right, so just to summarize that, of the total yearly evaporation, 84% comes from the oceans and 16% from the continents in terms of contribution to evaporation. 75% falls back on the oceans and 25% on the continents. And during the year, that atmosphere transports 9% of the ocean's evaporations to the continents. So only a small amount of that ocean evaporation makes it back to the continents. It's pretty crazy. And then, of course, this water goes back to the ocean via streams and then groundwater. It's kind of an interesting thing. I read a study about how when the Front Range developed and agriculture developed, people irrigated more, right? So you've got more evaporation happening. It's called evapotranspiration, referring to transpiration through plants. So when you introduce more irrigated lands, there's more water vapor going into the atmosphere, and the thunderstorms and rain events became more severe downwind on the plains. So if you go eastern Colorado, their rainstorm events became more severe because there's more water vapor locally being evaporated upwind from the Front Range. We're going to talk about some basic water balance now. Let's see, didn't bring my time here. Here we go. We're 20 minutes in. We'll go another 10, then we'll take a break. So when we talk about a reservoir, this could be an actual reservoir. It could be a groundwater basin, could be a watershed. Reservoir is a generic term here. And it's just a place where storage happens. So it's got a volume V. And we have inflow I and outflow O. And at steady state, the change in volume in our reservoir with respect to time is 0. So what's coming in is equal to what's going out. So you've got some real quantity of storage in there. And then you can calculate the residence time simply as the volume divided by the inflow or the volume divided by the outflow. And that gives you a rate. Or not a rate, an actual time. So inflow is volume over time, right? And then this is volume. So residence time is an interesting term because we need to know how long water stays in a particular feature, a particular reservoir. So we saw that water balance, you have water vapor in the atmosphere, you've got water in streams, you've got water in groundwater, water in the ocean. An average molecule is going to have a certain residence time in each of those reservoirs. So just a basic calculation here. The residence time of water in the atmosphere. So we need to know volume, inflow, residence time. We're going to calculate this. Well, based on these average numbers, the volume is 13,000 cubic kilometers of water in the atmosphere. The outflow is from precipitation, and these numbers we got from that figure previously. So we have 297,000 cubic kilometers raining over the ocean, and then we have 99 raining over the continent. So this is our outflow, 396,000 cubic kilometers. So to calculate residence time, we'll take our volume divided by the outflow. If you do our units, we've got cubic kilometers per year as the denominator, and we've got cubic kilometers in the numerator, so we end up with a time. So the average residence time of water in the atmosphere, again, average, right, is 12 days. And so that means, on average, if you divide the year by that, the water in the atmosphere is exchanging 30 times a year. Of course, that's going to be different locally. So you could try this calculation yourself for the residence time of water in the oceans. Here's the ocean volume, 1,370,000 times 10 to the 3 cubic kilometers. And this is our evaporation. So why I use the ocean through evaporation. And we can calculate our residence time in the ocean. Much longer. The average molecule of water is spending 4,100 years, 4,000 years in the ocean. That's some old water. So here's some typical residence times in glaciers, hundreds to hundreds of thousands of years. You can imagine Greenland that's got miles of ice. That water has been in there for a while, although it's coming out much more quickly these days. Oceans, 3,000 to 4,000 years. Rivers and lakes, days to years. Groundwater could be years to millions of years. So some groundwater is super old because it was deposited in this aquifer during some other geologic age when a river or a lake existed where now it's gone, right? That's called fossil water, and there's a lot of fossil water in the Middle East. So where they used to have, lakes and rivers, now they're desert. So a lot of their water is coming from water that's no longer being replenished actively. Okay, here we go. Okay, so we will talk about what a watershed is, and then we will take a break. Now, who has not heard of the word watershed? Okay, so watershed is, maybe could someone else tell us what a watershed is from what you know? What do you know about watersheds, Dylan?
From my words, I would say that a watershed is a particular area that encompasses everything that water can shed down to. So if you got a river down the bottom, you look at every drainage that's coming up out of that river, and then you're collecting water from all those drainages that comes down to that river.
Yeah, exactly. So it's a topographic feature. Topography meaning the shape of the land. And the way our world works, water falls on our planet, and over time it erodes the soil, the rock, etc., to create drainages or watersheds. So drainage or watershed, catchment is another term that I think the British like to use. Cuenca in Spanish, I think there might be some other words, but it's the area that captures water, and any raindrop that falls in this boundary will run into a creek, into a river, into a lake, and have a common outlet point, be it the ocean or a tributary with another stream or something like that. So you can imagine that watersheds are scalable. You can have a teeny tiny little watershed. CMU is a kind of a watershed, right? When Carrie, I don't know if she's told you about her wastewater surveillance that she's working on. I guess some of you guys are actually working on that. She had to figure out what the sewage watershed was for campus. So it actually doesn't necessarily run with the topography, although it's pretty flat here, right? But the pipes, they start at a certain elevation, go to another elevation, they collect other pipes. And so she's figuring out which dorm, which manhole is the outlet point of the watershed, and then which dorms are inside that watershed. That's kind of a weird or a different way of thinking of it, but there's obviously engineered watersheds, and then there's like the landscapes watersheds. Urban watersheds can be complicated too, because in urban watersheds, maybe you've got the watershed boundary that you would see from the land, from like a topographic map, but then you've got a storm sewer coming in from a parking lot nearby, and so your urban watershed could be augmented by whatever engineering conveyance structures have been put in place. So here's the EPA's definition. The land area that drains to a common waterway. This is from a textbook, an area that contributes water to a particular location on a channel. So watersheds have different parts. When you're high up in the watershed, you're in the headwaters. Colorado is a headwaters state. You know what that means? What does it mean to be a headwaters state? Yeah, we're at the headwaters. So, the Rocky Mountains supply water for the Colorado Basin, right? Colorado River. And that water goes all the way down to California and Mexico. So So we're in the headwaters, the little snow falls here, and that water then goes all the way down to supply everyone along the way. So kind of midway or downstream, it could be on the main stem. So the main stem of the river, the Colorado River is a main stem. And then you have an outlet at some point. We could define an outlet as just where the Colorado and the Gunnison meet. It could be where the Colorado meets well, it doesn't really have an outlet anymore because it's sucked up, but it used to drain to the Pacific Ocean, and that would be the outlet there. This is a fellow from our history in America, John Wesley Powell, and he was actually one of the first white people, at least, to navigate the Grand Canyon in a boat, a wooden boat. They almost died, but none of them died who stayed with the mission, and they got through the Grand Canyon in the late 1800s. He envisioned the West as not the states that we have today, but a series of watersheds, because he knew that water is so critical to developing the West, to civilization in the West. And so he envisioned a way that we had these drainage districts that he wanted to see. And these drainage districts would have the water within a watershed kind of used within that unit, within that topographic unit, rather than what we have where Colorado sits somewhere around here, and you've got the Platte Basin on this side, the Arkansas Basin, you've got the Colorado Basin on this side, and it's a bit of a mess, right? There's a lot of developments, water usage on the Front Range, a lot of transbasin diversions, bringing water from the western slope over to the Front Range. And then you've got all these states, all these compacts between the states to make sure that Colorado's water is shared. We have to share the wealth. So I don't know that his vision for a watershed-based administration of the land would have worked because of politics, but it was another way to think about how we manage our development, our civilization in the West. Powell also founded the USGS, the U.S. Geologic Survey, which is pretty cool, or at least helped found it. So watersheds are categorized, cataloged of hydrologic units. Hydrologic, let's see. Oh yeah. So we'll talk about what that means. But you start with these numbers, right? And every major basin has a number. So here we are, Upper Colorado River is 14, Lower Colorado is 15. And you can see Colorado being the headwaters, we share the Rio Grande, Arkansas, the South Platte goes into the Missouri River, which goes into the Mississippi River. So we've got quite a few watersheds that start here in the Rocky Mountains. But as you can imagine, watersheds scale. So you have big watersheds as continental watersheds, and then you have what's called the HUC 8 cataloging units, hydrologic unit code. So HUC, you might see that. These are all the HUC 8s, and so you've got the big region one. So Colorado, Upper Colorado is 14, sub-region number, and then it goes on. And so the longer the number, the smaller the watershed. And they've actually gone down to the HUC 14. So that's a kind of a tiny watershed, like Canna Creek up on the mesa would be the HUC 14. So here's a look at 2,264 of these watersheds across the country. And why do we need to do that? Why do we need a number for all these watersheds? Well, we got to keep track of things. We've got the Clean Water Act, which has regulations on rivers and water quality. We've got EPA regions within these. We have Army Corps of Engineers as a permitting system for wetlands. All those are based on these units. And so there's a lot of like policy and regulation related to knowing where you are and how laws apply to these regulations. So here's a look at all the HUC 8s, the 8-digit codes for Colorado. And eventually these might, if they're not familiar with you already, you'll get to learn these over the course of this semester, and just if you stay around Colorado. Here we are in Grand Junction. We got Glenwood Canyon, the fire's happening, the Colorado headwaters. This is probably the most scrutinized watershed in the country in terms of water supply. The Gunnison and the Yampa come together down in Utah and become the Colorado. So these are tributaries. And then we've got the Green River up here. That's also a major tributary that goes into Wyoming.
This map, all where the river's crossing the boundary.
Oh, do we look at that? Yeah, the Dolores. I never figured that out. Oh yeah, so what happens is, so these are, okay. So these are the state Division of Water Resources boundaries. And they put Dolores and San Juan together. So there's a watershed boundary right here. And the Dolores River comes in with the, yeah, so you know what I should do? I need to correct this map because these are not actually HUC 8s. This is how the Division of Water Resources manages things. So yeah, so there's a watershed boundary here. This is the San Miguel River where Telluride is. The Dolores comes in and then it becomes the Dolores River and it meets up with the Colorado. And then you've got the San Juan and all of its tributaries which go down and then eventually through New Mexico meet up with the Colorado down here. So these are all Colorado River. This is the Rio Grande, which is its own thing. Then the Arkansas and the South Platte both go into the Mississippi River. Okay, so let's take a break and then we'll talk about how we draw watershed boundaries. I'm gonna go outside and get some fresh air, get a drink of water real quick. I'll be back in 5.
Yeah. Hot.
Really hot.
Yeah. Yeah, I'm ready to wear my sweatshirt.
It's pretty terrible. What's different? Yeah, he hasn't taken hydrology yet.
He was in
Yeah, but he wasn't in there.
there. I don't know, this is I know it's with this kind of story confused. It's hydrology.
Yeah, plus Dylan minus Michael. I think Michael's.
High school.
I thought this was started at 2:30, wasn't it? At 2:30, like before. I heard for 2:30.
I don't think so. Are you in Fairmount? Or anything?
I'm in all the classes you guys did last year, fall semester.
You didn't take intro to construction? I thought you did.
That was the only one.
Did you take construction last semester?
I took it from
Electronics.
electronics.
You're bolder now?
You took GIS, right?
Uh-huh.
That was
Must be fun stuff with like GPS surveying.
Yeah, we should
towards
probably,
the end.
all the people taking.
What?
Everybody's taking transportation stuff, and yeah, because it's an elective,
Uh,
they're both electives.
Are you taking both of them?
Yeah.
You're getting your electives knocked out.
Well, you know, I haven't took concrete one, everybody did last semester. I took family stuff, concrete one, which is okay. So I still have to take more elective. I don't know, I might take concrete next semester, just,
Interesting class. I like
I think it's useful, that's why I might take it. We'll see. If there's another recollective. But you'll be gone.
Don't have to listen.
I don't fail anything.
That's sad.
Yeah. I think course it only has to pick one class.
How do you take still design without passing structural? That was a prayer.
Well, I mean, so he was already registered for those classes. He was a concrete kid. Like overrated.
Wanna be like Jacob? Jacob passed. Oh, he did? Yeah, he talked about it, went to it.
Who's Jacob?
Jacob Dexter, you know, hanged out with Jack all the time.
Was he gonna fail and not being able to graduate?
Oh, he had a 68% in the class. And then apparently a lot of people did not very good in that class online. So they
Oh, last semester?
But that is 69% a year. It wasn't online. Really? Sure.
I thought I was gonna fail it last semester too online.
Online thing.
Somehow I had a 72 and somehow when the grade book came out, I had a B. I don't know how that happened, but I had a B.
That's probably,
Well, I did pass a bunch of people who's like, it's probably why you go to school now. That's not fair. We all get this.
Yeah, but you had 72, there's no way above you 8%.
Well, I think you like curve something and then check after that.
Oh. Yeah, I'm not looking for it.
The private owner own like, I don't know, like build a dam and own their own water supply.
Only if you have a water right. And let's see, will I talk about water rights? I can share some, I think we might talk about water rights. Yeah, I mean, I think we need to, right? It's Colorado.
And shares and all that, are we gonna go over all that?
You know, maybe I'll have someone come in and talk to you guys about it, because there's obviously a rich history of water rights, diversions, water irrigation associations, you know.
need that lawyer from Youth Water. Talk to the conference for that class.
I might try.
Cause he like knew his stuff.
Yeah. There's a lot of good people. So maybe I'll make that happen. I think that would be helpful, because that's like water in Colorado. It's based off of this crazy laws and old laws, and it's pretty complicated.
I'm asking the company that I work for right now, the house that they're working on, they're gonna build a dam to make like a little beach pond.
Uh-huh.
So that's why I was asking.
Okay.
Like a private farm.
They would probably have to get a permit through Division of Water Resources for that. Whenever you build a structure that changes how water moves, basically that's retaining water, right? Because you're retaining water, you're increasing evaporation around the pond, you're increasing infiltration down below, so you're changing the water balance locally. And if there's someone downstream with a water right, they could contest that and say, hey, you're harming my water right. So not only that, but then anytime you put in something in a stream, you have to get a Army Corps of Engineer permit, so a wetlands permit. So you can't just do that willy-nilly. When you're impacting a waterway, a wetland, a stream, you have to get permitting for that as well. So, yeah, in Colorado, that's nationally, but in Colorado, you've got the water rights issue whenever you do that. Hey man, I'm talking with these people right now about, so I do stream restoration, wetlands restoration, and when people want to restore wetlands, like up in the headwaters somewhere, a meadow that was, the channel was messed up and channelized, and the water table drops and everything turned dry. They want to restore that for habitat, trout habitat, endangered species, whatnot. The Division of Water Resources here that manages water rights is concerned, because now you're raising the water table, more plants are growing, you're evaporating more water. And so even at that level, people are concerned about water rights. So it's pretty intense. Okay, so let's talk about drawing watershed boundaries. I gave you guys a handout, and we've got a little watershed here. This is Sheep Creek, Colorado, probably 20 sheep creeks, sheep mountains. And here's what the image looks like, kind of hard to see here on the PowerPoint. But you've got a creek, and then you've got a bunch of tributaries coming off. So we're going to look at this particular tributary, zooming in, and talk about how to delineate that watershed. Okay, so find this point on that printout that I gave you. That's kind of a little bit further to the, I guess, left. And that's going to be our watershed outlet. So there's a blue line that kind of comes up from it. And maybe you can trace that too, just to kind of have a reference of where the stream actually is. It's called our watershed outlet, also called a pour point. If we're pouring water out of the watershed, that's the point that everything pours through. That's kind of a modeling term. Did everyone find the outlet? All right, now we're going to look at these contours. So this is the USGS map. It's got contours. The contours show areas where the elevation is the same. And so it kind of helps you visualize the landscape. And the way topography works is you've got kind of legs, right? These water is going to flow between these legs. There's a little bit of blue humor here, but if these are legs and you're peeing, water's coming out between the legs and going downstream. So that's just a way to remember that, hopefully, for a mnemonic device. Because it can be confusing. You don't know which, this is another area where the contours are going like that. This is a ridge though. And so if you can see, this is high elevation and low elevation. Water is not going to go along the ridge. It's going to go through the valley. So that's how you identify valleys, is by knowing where the elevation's dropping kind of between the legs. All right, so that's another step, is to orient ourselves. Okay, so we know we're in a valley, water's coming through the legs, right? Now we need to find the upper edge of that, or the boundary of that watershed, the ridge line, so to speak. And so we're going to find the high points. So I've identified these high points, and these are usually, you can see them as kind of like peaks, right? A little circle that is the top of the contours, the top of the peaks. So find all these peaks around your stream. Some of these are actually been surveyed, so you've got a little X and then an elevation right there. So these peaks will kind of connect the dots, right? We'll know that between a peak, we have a saddle. And I'll just go back. A saddle is a low point, or a pass, you can think of it, right? If you go hiking in the mountains, you go over passes. It's also known as a saddle. It's the low point along a ridge between two peaks. Okay, now we want to know that we want to find what's in our watershed and what's out of our watershed. All right, and the way to do that is to think, well, we know that water, whenever it rains, it's going to flow perpendicular to the contours. That's the shortest route downhill. So perpendicular to the contours. It's raining right here. Water's going to move this way. It hits this peak, it's going to move this way. Hits this peak, it's going to move this way. Hits this little hill slope, it's going to go this way. And so if you draw these little arrows, it'll help you identify which way water is shedding, and is it in your watershed? Is it in your drainage? The hardest part, I think, for delineating watersheds is really these kind of boundaries closest to the outlet. This is a ridge line right here that's coming down, and it's trying to figure out, well, you know, which way is water going? So I got to say the water on the ridge is going to go kind of perpendicular to the toe, but everything's going to kind of come this way towards the stream, and everything's going to come this way. So we'll draw our little water lines, and then we'll figure out, okay, based on the water flow paths, what water is actually going to go into our stream versus out of our stream. So here's a ridge, water's flowing towards our stream. Here's another ridge, and water's flowing towards this stream. So this one's out. We're not going to include this in our watershed. You can see down here, this is going to be outside of our watershed because it's a little tiny drainage away from the creek. Same with this one. You can identify your boundaries, kind of be to the side of those arrows. And now we're connecting those dots, and we're making sure that our boundary excludes the arrows that are going away from our stream and includes the arrows that are going to our stream. You don't need to necessarily do this every time, but this is, I'm doing all these arrows and all these steps. This is kind of a way to walk you through how you get to an actual watershed boundary.
So this is a quick question.
Yeah.
So both on the left and the right of that watershed right there, I guess the right side is a good example. My question for the left, but there's that little tiny drainage coming up out of the creek right there on the right side.
Like this one?
Yeah, just that little guy right there. I mean, you can just define that as a watershed.
So it's got its own watershed, right?
Right, because it's so small. Okay,
Yeah.
so now when you look on the left side, that, I mean, does that have its own watershed, that little tiny one right there? Because that kind of bends around from that other watershed to the watershed we're looking at right there.
Yeah. So
So
everything has a watershed.
right. So is that a little one right there in between the two?
Yeah. So let me just get those arrows out of the way. So this little guy, you know, it's not a high resolution to really see. This little guy's going to have a watershed. Maybe it's like, I don't know. I'm not going to be able to like do it off the fly, but this guy's watershed is going to be something like that. This is a little watershed right here. Watersheds could be, I don't know why you need to do this, but it could be a meter squared. It could be an acre. It could be 10 acres. It could be a mile, or multiple kilometers squared. So, we talked about the big major river basins and then the Huck 8s, right? The river basin has many of those Huck 8s. You can keep going smaller and smaller and smaller. And so this is Sheep Creek, and this is just some tributary that probably doesn't even have a name, right? The Sheep Creek's watershed encompasses all of these little tiny watersheds. And we're going to use a tool, an online tool called Stream Stats, to basically they've got all this digitized. You click on a point on a stream, it finds all the pixels upstream of that. And so you can delineate a watershed depending on where you click on the map. If you miss the stream and you click over here, it'll give you the little teeny tiny watershed over here. But if you click on the stream itself, it'll give you the whole big watershed upstream of that. So I picked this little tributary just to show you. I could have done it for this one, could have done it for this one, I could have done it for this one. All right, so now we're going to think about the balance of water in a watershed. We're going to assume steady state, so the change in storage over time is going to equal to 0. But if we put like a control volume or a box around this watershed, we can think of, well, we've got precipitation, P, coming in, evapotranspiration, ET, coming out. We've got the stream flow coming out, that's Q, that's the surface flow. And then we've got groundwater. Groundwater could be coming into a basin because, you know, the surface watershed could be different from the groundwater watershed. Typically, that's negligible, or we kind of ignore that. And we think about groundwater coming out, certainly that's important. And then you've got storage, or S, the water that's contained in the surface and the subsurface, the streams, the lakes, the soil moisture, and the groundwater. So those are all the main components of the water balance of a watershed. So on average, if we kind of ignore the groundwater, if we say this is pretty small relative to the surface water, is that groundwater moves really slowly. And so the rate of groundwater coming in and coming out is pretty small. So if we ignore those parts, we can simplify it into the precipitation coming in is equal to the discharge and the stream flow and the evapotranspiration. And if we think about all the watersheds in the whole world, this is what the average water balance is. So 800 millimeters of precipitation on average annually. This is how much is running off, and this is how much is evapotranspiring. So if you look at the runoff ratio, which is how much precipitation comes in and how much discharge goes out, that's 39% or about 40%. Obviously, this varies a lot. And we'll be talking about runoff ratio in Colorado. So again, it's the ratio of discharge or runoff from rivers to the precipitation coming in. So what does it mean that this ratio is 40%, Val? If 40% of the rainfall comes out in the rivers, yeah, and mostly we're assuming based on this equation that it's evapotranspiring, right? Mm-hmm. But with when we have a drought, when we have climate change, there's regional variability in this. At the same time, these can change. This ratio can change, and how much runoff we get. You could also think of it as water yield, how much water a basin yields. That's a really important number that we think about because this is our water supply. This Q is the water we have available to use. Just another look at a watershed from the multiple dimensions that we have. We've got the Q coming out in the rivers, we've got some infiltration, we've got shallow groundwater, we've got deeper groundwater, different aquifers as well. Okay, so what does this look like on the ground? Does anyone recognize this watershed? Canna Creek. Looks better on my screen, it's a little washed out. So here's the Canna Creek watershed. This is on the Grand Mesa. If we were in a different classroom, we could kind of see it from here. There's the Trails End Road that you can see from Confluence Hall, and Canna Creek's kind of tucked behind it. So here's the watershed, and it's an important watershed. Do you know who uses this water that comes out of here?
Does you do it? Or?
No, so City of Grand Junction.
Okay.
Ut's water supply is back on the other side, kind of near Coal Run.
Okay.
They got a bunch of lakes up there. Plateau Creek watershed. So Grand Junction, City of Grand Junction's water supply, and this actually used to be a lot of the water rights associated with this were agricultural water rights, and the City of Grand Junction used eminent domain to forcefully purchase those water rights from the farmers. So some bad blood there historically. And we've got a ton of lakes up here, a ton of reservoirs up here, and a lot of snow obviously falling on the mesa that supplies this. So the snowfall comes down, most of the precipitation comes with snow. They do get rain this year, not a lot of rain. So that snow comes down, and mostly it falls in these upper areas, right on the flat part of the mesa, and then a little bit on the hill slopes. All right, that snow melts, the sun's out, we get sublimation, which is actually going from snow to gas to water vapor. So it skips the melting part. So that happens. So we lose a lot of snowpack to sublimation. But then when it melts, we have evapotranspiration. So in the springtime, all that snow is melted off, the ground is soggy, then you get plants growing trees, and that water exits the watershed through evapotranspiration. We also get surface and subsurface runoff. So the creeks are filling up in the spring and running, and then that water infiltrates down into the ground as well. So we can measure all these components and kind of track what's happening. We've got the Natural Resources Conservation Service, NRCS. They have a SNOTEL. This is called snow telemetry. We'll talk about this in more detail in a few weeks. But they're tracking. They've got 2 sites on the Grand Mesa, and then hundreds of sites scattered across the West and Rocky Mountains. And they track snow water equivalent, so the depth of water that's stored in the snowpack, that's the blue. They're tracking average precipitation and actual precipitation. And then they compare it to the median, which is the red one. So this is 2019, 2018 snow season, which is pretty good. And you can see that the snowpack is above average, and then it took a lot longer to melt. So this is when the snow on average leaves is a little bit by the end of May. And here the snow stayed on well into June in that particular year. That was a big snow year. So then we've got USGS gauges. Unfortunately, the Cannon Creek one isn't running anymore, but the city keeps track of the water. And then you can look at the stream gauge. So how much cubic feet per second is coming out of the creek, and relate that to the snowpack. We'll actually have a homework assignment where you look at all these data together.
Use the median rather than that one.
Yeah, I would say the reason is because the median is often used, and that's because you just have a lot of variability. And so the mean value we know is skewed by very high numbers and very low numbers. So the median is a more stable value. It's always going to sit 50% of observations above, 50% of observations below. That's a typical metric that people use. So let's just look at some other kinds of data we have. Okay, yeah, almost done here. USGS gauge, we're going to talk a lot about stream gauge data. There's the Colorado River near the Utah state line. If you guys were on stats, right? You did not stick around, which is great. Sad for the class, but good for you. We talked about this stream gauge. I think we looked at the stream gauge and some homework or something like that. It's showing you the daily observations or 15-minute observations, and it's showing you the median statistic for that particular day across this year. So this is a hydrograph, so a graph of water, of hydrology, and we'll be talking a lot about these. There's kind of a seasonality to this. You can see it gets low in the fall and winter, it gets high in the spring and summer. This is when you put a bunch of hydrographs together. So we've got 1 year's hydrograph is this way, and then you've got the day of the year from January to December 31st. And so you kind of see these mountains of putting a bunch of hydrographs in 3 dimensions. And we've got, I guess I don't have what these different rivers are, but this is kind of like a snow melt system that, you've got a big peak in a certain time of the year. This is kind of a system that doesn't really change much over time. It's just kind of random white noise. Here's a system that gets a lot of big storms any time of year. So there's a lot of different kinds of shapes and seasonalities to hydrographs. Okay, last kind of topic we'll talk about, and then we'll talk a little bit about the project. talk a lot about surface water. We're going to spend most of our time talking about surface water, but groundwater is really important. Here's a picture from one of these James Bond movies with Daniel Craig. I think it was like the second one, Quantum of Solace. And they're in the desert, it's like a lithium mine or something, and then they find the aquifer, the underground aquifer, and it's this lake and a cave. And I think a lot of people think of aquifers as like this pool of water sitting somewhere. But aquifers are really just water that exists between soil. Maybe it's sand, maybe it's sandstone, maybe it's clay. An aquifer is really just soil or rock with water in the pore spaces. And we typically access aquifers by drilling a hole or a well down into that and letting the water in these pores infiltrate into this pipe. And then you pump it out. So we'll talk about the properties of these grains and how water flows through it, and how we can calculate how fast and how much water flows through aquifers into wells. All right, so our class project is going to be based off of this software called HEC-HMS. So HEC is Hydrologic Engineering Center, Army Corps of Engineers. So it's this group, they're in Davis, California, and they make software for water, typically water users. So they make a lot of different kinds of software. It's free, it's from the government, and this one's pretty old school. Actually, they're all pretty old school. They haven't been, like the GUI has not been updated for like 20 years, right? They're always doing little updates. It's a little bit buggy, but that's what comes with free software. And the HMS part is hydrologic modeling system. So we're modeling hydrology. This modeling platform, this software can do a lot of different things. We're going to use it to do a very specific thing, which is calculate a stormwater hydrograph. And it's got these basins, so these are watersheds that you can visualize. You represent them as this little kind of node, and you connect things together. So this is connected to this is connected to this. You've got all these sub-basins working together. You put a rainstorm on it. You say it's going to rain 1 inch over 2 hours. And then it uses all these components to calculate what the runoff hydrograph is going to look like at the outlet of that watershed. And we'll be interested in the peak discharge. We'll be interested in the volume, how long it takes between the rain event and this peak. So there's a lot of components of that we'll cover. And so there's going to be a bunch of different components to the project. We'll start with a watershed and channel network delineation. So this is kind of the topology of your watershed. So how many streams do you have? How long are they? And how do they all work together? Then we'll do the meteorology and precipitation. So the design storm. How do we represent rainfall? Basically a fake rainstorm over this watershed. It's going to have a depth, a distribution, and time and space. And then once you get that rainfall, you're going to have to model how it runs off. So some of it's going to go into the ground, some of it might evaporate, some of it's going to flow over the ground and into channels. And there's a lot of different ways we can represent that from an engineering standpoint. And then once it meets the channel, you've got to route it through the channel. So routing just means flowing through. And there's different ways to represent that. We'll talk about some different methods that we use to estimate how long it takes for a flood wave to move down a channel and what happens to that flood wave as it moves through the channel. So these all will track, these are components of the project, and they'll track with where we are in the semester. So we'll be learning precipitation. We're doing watersheds right now. That'll be the first part of the project. Then we're going to learn precipitation. That'll be the second part of the project, and so forth. So you put all these components together, and then at the end, you'll have a final report that you've been building along the way. Okay, so we got some readings for this week. I've posted a chapter. This is not the textbook for the class. It's I just think they do kind of a better job of doing introduction stuff. So chapter 1, sections 1.6 to 110. and then 1.13. There's a lot of like equations in there, so don't feel like you got to read that. Just like skim it for the ideas, the concepts. And I've also posted an article that features the Western Slope. It was just published this month, Washington Post. Pretty interesting read, not super long. It's called Colorado's Lost Water, the Giant Climate Hotspot is Robbing the West of its water. So the main takeaway here is that when you look at global climate change models, it predicts on average a certain amount of heating effect per year. The area in the Western Slope and into Utah, the kind of Colorado Plateau area, is warming faster than that, right? So there's the global average, and then there's what's happening regionally. And so this explores the kind of human impacts and societal impacts of this observed trend. So you can look at that online. I've also made a PDF of it if you can't access it for some reason. Washington Post article. And then on Thursday, we'll have a short quiz at the end of class based on these two readings. So this is, does anyone recognize where this is?
Delta and White pretty much.
Yeah, exactly. So I think this is the Grand Mesa, I'm pretty sure. These are the, I don't know what they call them, but the less Grand Mesas. It's like a plateau, and I think this is like the Creek Valley that goes up, maybe like between Orchard City, like if they're drive up to Orchard City on the south side of the Grand Mesa. So this is basically like the south side of the Grand Mesa near Delta, just outside of Delta. And that's the dude's ranch. He's looking down at it, and he's probably sad. And he doesn't have a lot of water. I think this is Surface Creek. That's what it's called. Okay, so homework 1 is also posted. It's going to be due next Thursday. So you get a week and a half just to get you guys warmed up. Usually give you a week, so give you a little bit more. It's on Canvas. You're going to delineate and explore some watersheds, and you're going to do a water balance for the Mississippi River for the 1993 flood event. So I give you some data, and you're going to do a spreadsheet exercise on that. So that's on Canvas. Check it out. And that's it, guys. Look at that, 314.
Right on the money.